this for 50 years, so, you know.
Okay, so let's have a look here. So, oh, what happened? This isn't how it's supposed to work. Kind of did. Back in business. Okay, scoot forward if you can. Scoot on up. You're gonna want to see this. We got cool stuff to talk about today. So we're gonna look at Newton's third law. So now let's quickly review. What are Newton's first and second laws? First law, law of
Inertia.
inertia. Okay. Then we talked about that, right? Objects at rest tend to remain at rest. Objects moving in straight line motion at constant speed tend to remain in that state unless acted on by an external force. Okay, so Newton's second law, summarized by a simple equation, F equals ma. Net force equals ma, right? Okay, Newton's third law. Newton's third law is kind of a fun one. This is one that sometimes people conceptually have to think about a little bit before it makes sense. So this is the way, this is like a game show law. This is one, if you're ever on Jeopardy or something, this is one of the ones you're going to get asked. And this is the most common way that we describe Newton's third law. You've probably heard this. For every action force, there exists an equal and opposite reaction force. I don't like that one very well. I mean, I guess it does the job, but I like something like this a lot better. I like to think of it this way. Newton's third law, this is a better statement in my thinking. Forces occur in action-reaction pairs that act on different objects, are equal in magnitude, and are opposite in direction. Okay, and that's, you like the first one better?
Me too.
Okay, the problem with the first one is that sometimes people, they misapply it in a way that I'll let you trip on it yourself here in a little bit, maybe. Okay, so one way you can think about this then, you can describe it this way. You could say that this could describe the action-reaction forces. I really don't like the idea of action-reaction forces in a way though, because it makes it sound like one of them is primary and the second one is just a reaction to that primary force, and it's nothing like that. They are literally the same force pair, just applied to different objects. And so you could call either force the action force or the reaction force. It makes no difference. But a lot of times the notation we'd use is we'd say something like F sub AB or A on B. So this means that there's a force acting on B due to object A, right? And then the reaction would be negative F B on A. So negative meaning they're in opposite directions. The force acting on B produced by, or actually acting on A produced by object B, okay? So think about it this way. Neither causes the other, right? They exist together. They either both exist or neither one does. There's no such thing as a force acting on a single object only. It's impossible. It'd be like the sound of one hand clapping. It makes no sense, right? You have to have two objects in order to have a force pair. You could talk about, like, if we've talked about this in the past. If there is a closed system, then external forces are forces that are outside of that system, right? I think we use an example in here, like if you're driving in a car and you push on the floor of the car to try to slow down, it's really not doing any good because that's internal to the car, right? The only way you slow down is if you provide some force external to the car, which is tires on the road, right? Different systems can interact via action-reaction forces, though, an action-reaction force pair. Right? So there's all these internal forces inside the system of the car, right? You could be driving the car on a ferry boat, and then on the ferry boat, that's another system, and there's going to be some forces that act between the system of the car and the system of the ferry boat, right? And what would happen if you, well, we'll come back to that one. We'll come back to that one.
Where you go back to the equation on the first page.
Sure. And I'll put this up on, I'll put all the notes up too. I'll put this PDF up, so it'll be there. Okay, so let's maybe look at a couple examples here. Like what if let's take something really simple. So if I hold this mass in my hand, can somebody tell me what's an action-reaction pair? Forces acting there.
You holding it up and grabbing it.
Okay, so we could say, for example, here's the suggestion. that there's the weight of the object pushing down and my hand pushing up. Is that an action-reaction pair? It's not. See, that's the problem with saying action-reaction pairs, because it seems like they're equal in magnitude. That's true. The weight and the normal force applied by my hand are equal in magnitude, but they're not an action-reaction pair because they're acting on a single object. Action-reaction pairs have to act between two objects, right? The weight is acting on the mass. The normal force is also acting on the mass. Those are balanced forces, so the net force is zero, so there's no acceleration, but they do not comprise an action-reaction pair. They don't fit either, because they don't match the pattern. Think about the pattern. If the action force is A acts on B, then the reaction force has to be B acts on A. So my hand pushes on the mass. If that's A acting on B, then what's going to be the reaction force to that? My hand pushes on the mass. The mass pushes on my hand. Okay, that's an action-reaction pair. Okay. What about the other one? We talked about the weight. What's causing? So what's pushing on what there? Okay, gravity. But when you talk about gravity, once again, forces have to act between two objects. So what's pulling on the mass in this case? When you say gravity, you're really implying something. What's pulling on the mass then, on this black mass that's in my hand? Something has to be. Earth is, yeah. It's the mass of the Earth is creating a gravitational force that pulls on this mass, right? Okay, so then what's the reaction force?
The black thing pulls up on Earth.
The black thing pulls up on Earth, exactly, right? Black thing pulls up on Earth. So then, try something here. Just everybody real quick, try, I'm gonna go ahead and see if you can notice this. Okay, close your eyes real quick. Okay, just as sensitive, you gotta really pay attention here. See if you can feel this, okay? Ready? Count of 3. Did you feel the Earth rush up to meet this bottle and I let it go?
No.
You probably didn't feel that. How come?
Because the equal forces in comparison there.
The mass, right.
So much more huge.
Okay, so much larger mass. The little bit of, it would just be absorbed by a little bit of deformation in the rocks and things. But you could, I mean, if you wanted to get really exotic, if you took some material like from a neutron star. In a neutron star, if you look at just a, I guess I pulled this up a little bit ago. What was the statistic? This was really impressive. Yeah, so if you take like just a little matchbox, you know, I mean, like just, you know, those little tiny cardboard boxes that have matches in them. If you fill that up with the matter from the neutron star, that would be the equivalent of about 6 billion tons of Earth. Okay, that's the mass. It would be the equivalent of like almost a cubic, I think it's almost a cubic kilometer of Earth would be required to have the same mass as that tiny little bit of, you know, matchbox-sized piece of matter from a neutron star. It's exotic matter where all the space in the atoms has been squeezed out. So if you were to do something, now you would notice this. If I had somehow the ability to, let's say, take let's say we're going to take a beach ball size piece of neutron star material and drop it from somewhere, you would notice that. You would notice that the Earth would recoil a little bit. There would be some, now you wouldn't want to be any place around that because the strength of gravity in the vicinity of that thing would be, you know, billions of times more powerful than the gravitational force that you experience on the surface of the Earth, and so you would just be ripped apart. You'd be spaghettified if you're anywhere close to it. But ignoring that, what would happen if you did drop that thing somewhere into the Earth, from somewhere into the Earth? What would happen? Yeah, it would just travel right through the Earth, right through the core, and pop out the other side, maybe slightly lower than the height from which you dropped it, but the little bit of friction would be so negligible compared to the vast forces going on that it would just kind of create Swiss cheese out of the Earth going back and forth through the Earth. And we did many, many times. And it would, I mean, there'd be more dramatic than that. You'd have gravitational, assuming that somehow we could guard against all the the earth that would just come rushing towards, I mean, really what would happen is the earth would just form some kind of oblong sphere of debris. It would not be good for the planet. But it would just keep going back and forth through the core, back and forth as the earth rotated. It would kind of describe a little bit of a curved path as the earth would be rotating, right? But you would notice that one because the mass is so great, right? The forces would be more on equal footing, okay? All right, so this is an example from the online textbook. So starting to look at some free body diagrams here. So if a person pushes off the wall of a pool, the part that we're interested in, the swimmer wants to get maximum push off the wall so they can accelerate forward with maximum acceleration, right? So what's really going on though? So the action-reaction pair is going to be swimmer pushes on wall. If that's the action force, what's the reaction force? Wall pushes on swimmer. So why does the swimmer push on the wall? They push on the wall in order to have the benefit of the return force, right? That's going to push them forward, right? The free body diagram, if we're just looking at the forces acting on the person, the force that we're really interested in is the force of the wall on the feet or on the swimmer, right? Technically, the same force is acting on the wall, which is rigidly attached to the ground, and so when the swimmer pushes off, the earth's just going to rotate back a little bit, right? You don't notice it, but it's there, right? And you can show that that's happening. Like if you're thinking about a car, if you lined a really massive car up on the ground and you accelerated forward, well, what are the forces acting? What's the force that's pushing the car forward? Tires are spinning. What's it going to be?
I'm not answer that question.
Yeah.
Is that how Superman goes around the world and
Makes it.
yeah, reverses time?
I'm not sure about the physics of Superman. I'm not sure when he goes around and makes it. See, I think that's a little hokey. I don't think that's quite in line with philosophy.
If there was a giant car flying around the Earth, would it?
If it was a giant car, anytime a car wants to go that direction, what does the car do? The tires push what? Yeah, tires push on road in that direction. Road pushes on car in that direction, right? And probably the most obvious evidence of that is when you can't push on the road very well. The road doesn't push on you very well. And if you're on ice, for example, what happens to the tires? And they just spin. They can't. They don't. There's very little friction, so they can't push effectively on the ground. Therefore, the ground returns the same weak return force to the car, right? If you're spin out in gravel, you can see it, right? You can see the gravel go shooting backwards, which is just evidence that we're applying a force to the surface of the road back in that direction, right? Rearward, and that pushes us forward. Okay, so
another question for us,
yeah.
Dan.
Mm-hmm.
So if he's jumping around the world, is he like messing up our orbit and all that? Because he obviously pushes against the Earth more than a normal person jumping around.
So the thrust of the rocket we watched, was that pushing the
Well, okay, let's go. Let's take the rocket for example. How does a rocket work?
Rush.
Okay, pushes against the ground, and the ground pushes up. Okay. Close, but not exactly.
Pushes against the air.
Ah, what's it push against?
Air.
The air? Well, how's it fly in space
Pushes against its own air that
then? No.
It sends particles backwards.
Ah. Okay, you could, if you were in outer space, and let's say that all you had was like a modern handgun that they've issued only to astronauts for outer space battles, I don't know what. But it doesn't require oxygen to ignite the powder. It's included in the, let's say the oxygen
It's in the
included in the rounds, right? If you found yourself that you drifted away from your spaceship a little bit, and you found that you'd forgotten to tether yourself off, and all you had was this special alien gun, what would you do?
shoot
Shoot in the other direction. That's a rocket, right? That's a rocket. Because what are the forces acting? You're pushing on the bullet, and the bullet, you can see that because the bullet goes flying away with very high acceleration. So if that's the action force, astronaut or gun pushes on bullet, what's the reaction force? bullet pushes on gun,
So
pushes
if
you back,
spit in
right?
that direction, it would also. Like,
So what?
If you spit, like if you
Yeah,
let go,
but you're in,
How
but
far
if
would
you
you
spit in
go?
outer space, you're just gonna spit on the inside of your face mask.
would that transfer at all? Would that transfer any force through the face mask?
No, no, because then it's gonna hit the face mask and pull you back that way. For a second it would, and then it'd be like, and then it hits forward, right?
Spit the other.
So, yeah. You could, I don't know, you could fart a little bit, right? But anyway, so,
Wouldn't that be trapped in the
it would, that would be bad.
Not necessarily
Yeah.
because the
Oh my
space
gosh.
debris.
But we,
tiny
we
bullets in the sun.
digress, I should, that's my fault, yeah, my fault.
Oh my
So that's all a rocket
Really
is.
accelerates.
Think about the molecules of exhaust as just being tiny bullets that you're shooting out the back of the rocket at very, very high speeds, right? And there's a little more to it. There's an equation called the rocket equation. It's not quite as simple as it looks because you're actually reducing the mass of the rocket when you shoot the propellant out the end. And so your acceleration is a little higher than you would normally predict because your mass is decreasing where the force is staying the same. So if you really want to make accurate predictions, you have to follow the rocket equation to figure out how fast you're going to go at a given time. But this idea that you're pushing on the ground is really common. I mean, you ask anybody that, that's what they're saying. That's what they're going to tell you, is that the rocket is pushing on the ground because we're used to pushing on the ground. If you want to jump in the air, you got to push on the ground, right? You can't just push on the air because you can't push hard enough or fast enough. But rockets can. In fact, the performance of a rocket is actually better in space than it is on Earth, because on Earth there's atmospheric pressure that's trying to force all, it's very slight, but the atmospheric pressure is trying to push all the gases back into the rocket, and so you have to work against atmospheric pressure to expel the gases. In outer space, you don't have to do that, because there is no atmospheric pressure, and so they're going to come out with a little extra velocity in outer space, right? So it's actually better to be away from, any kind of atmosphere or any kind of ground or anything like that. Okay? Yeah.
So say a rocket propels itself like 10 feet off the ground and then comes back down. Is there some sort of correlation between the force it took to get it up and the force it makes it down?
Well, sure, like if I were really dense, if I were made of neutron star material, or even more dense somehow, if I jumped up in the air, what's gonna happen? Well, as I jump up in the air, I'm pushing on the Earth, and the Earth's pushing on me, and so what we're gonna do is we're gonna do this, right? We're gonna come back together because we share gravitational force. I push on the ground pushes on me, but gravitationally, I pull on the Earth, and the Earth pulls on me. So once we're separated, we're both gonna still share a gravitational force that's gonna pull us back together, right? So yeah, the Earth would recoil, but it would also come back to meet me. And where would it come back to meet me? Exactly the same spot where I pushed off, right? Okay? We'll look at that from a different perspective pretty soon. Two different perspectives. We'll look at that from the perspective of conservation of momentum, and we'll look at it also from the perspective of conservation of energy. But this gives you an idea that would maybe, you can kind of see that maybe that would have to happen, right? Questions? Okay? So let's look at this car. If this car wants to experience a forward acceleration, there's a lot going on, right? There's a lot of different forces acting, and we've got to carefully choose what our system is going to be to weed out some of these things, right? So does this make sense? Let's look at all the action-reaction force pairs that occur, right? So what about the car in the road? What's the action-reaction pair going to be there? So let's just say let's say the car's in rest for a second. What are the vertical forces going to be?
Normal force.
Okay, normal force, yeah. So the road pushes up on the car with the normal force. What does normal force mean? Just perpendicular, right? At the same time, the car is pushing down on the road with the same normal force, right? So that accounts for, let's see, this guy and that guy, right? Does that make sense? Okay. But they can't act on the same object, right? Because it's an action-reaction pair, so it acts between objects. So one of those is acting on the car, one of those is acting on the road, right? Okay. What about the parallel or the horizontal forces acting between the car and the road? Well, we already kind of talked about that, right? The car's going to,
Friction.
Oh, good, car pushes on the road pushes on the car through friction, okay? So there's the road pushing on the car, there's the car pushing on the road, right? Okay, if we're only interested in the car, well, we really only care about those forces. And then there's one other action-reaction pair that's acting on the car, and you're used to this. If I asked you to draw a free body diagram of all the forces acting on the car, you'd be able to do that. And one of the ones you would tell, probably the first one you'd tell me is the weight of the car. Every time, that's the first one you've told me, is the weight of the car, right? So the weight of the car, that's a force acting between what? The car and the earth, yeah, car and the earth. So there's those action-reaction pairs, right? So there are the three forces that are acting on the, well, I guess they kind of forgot one, didn't they? This would be when they're maybe, no, I guess we're right. No, we're good. We're good. Yeah, we're good. Okay, so there are the three forces acting on the car, right? Okay. If we want to find out what the acceleration is on the car, we're just going to add up the net force on the car and divide by its mass, right? Because we know by Newton's second law that acceleration and force they go hand in hand, and they're just mediated by whatever the mass is of the object that the forces are acting on, right? So now what if we want to look at the road? Well, what are the forces acting on the road? The road's getting pushed backwards, right? And it's getting pushed down by the normal force of the car, right? Well, the road's really, I mean, we can take that as part of the earth, but if we want to look at the whole system, there are no external forces, right? The whole system, nothing's happening. If we're looking from outer space, we're not going to notice anything, right? But if we're just looking at the car, well, we notice quite a bit of, we notice that, yeah, there's acceleration, its motion is changing. If we look at just the earth, I mean, it's very hard to see, but technically it's there, right? It's rolling back a little bit when the car accelerates, yeah.
So is there a way to calculate what it would take in terms of a large car, like as its size, to cause the Earth to completely stop rotating? Like if every person go
A certain direction.
Well, we could do that, yeah. What let's do, okay, so here's a challenge for us down the line. Let's make the calculation of how many, well, you pick the car. How many cars, identical cars, would have to be lined up on the planet, pushing in the same direction and accelerating at whatever the maximum acceleration of that car is, in order for us to stop the Earth from moving? Okay, we'll do that calculation later. It's going to be a lot, though.
We should use the Impala because those are high torque and high horsepower.
Oh, Nick Oil, you need to give Mrs. Jones a
Model
phone
T.
about
I did.
It won't do anything.
that. You better go.
She said
I walked in. This is this.
Oh, it is. Give her, yeah.
So, because
Why don't you go, yeah, go ahead.
energy can never be created, technically every single thing that happens is from a perpetual, it's like a perpetual system of force and energy. Like, because the car isn't just moving, it has parts moving, which have to move because you made them move. And
Right.
you have to get in the car before that happens.
Mm-hmm.
And before that happens, you probably had to eat, and to eat, the plant had to grow.
Right.
But
So the question is, if energy is neither created nor destroyed, where does it all come from?
Yeah.
Okay. So it's just, the cards aren't dealt evenly. That's a great question. So what happens is, so this is another concept that we'll talk about a little bit later, but entropy is the tendency for things to become disordered in the universe. It's really just statistical, is all it is. But things always tend to go from an organized state to a disorganized state. So at the beginning of the universe, things were highly organized, the Big Bang, right? Since then, they've been getting much less disorganized, or much less organized. Heat is now being dissipated throughout the universe, and eventually the universe will die a heat death, or eventually entropy will fall to the point where there won't be enough energy invested in any one part of the universe to do anything. Like theoretically, if you wanted to live forever, you could never do that, because even if you invested your intelligence into a robot and the robot was gonna do your thinking for you, at some point, you could only think like one thought a year, or eventually one thought a century, because there would only be enough heat, enough energy for that to happen as entropy increases. So along those lines, then why do we get such huge concentrations of energy? Look at the Earth. I mean, we use energy like it's going out of style, right? I mean, especially in our country. Well, we do that because Earth because it's a planet, it's collected a lot of extra energy that's not, most of space is empty, right? But we got uranium, plutonium, and things that fell in from supernova, and they all collected in our planet. And so we've got this massive store of energy available that we're just gradually using up.
And the sun too.
And the sun,
That's
yeah.
a big one.
This one,
Part 2 to come, that was a great question.
Siler,
free body diagram, you have mg, force, normal force.
Let me turn this off real quick.